Hello everyone, welcome to AI Anytime channel. In this video, we are going to see that how we can measure the memory consumption of large language models. So when you inference, run or fine tune an LLM, it has some memory consumption associated with it and it has direct influence on carbon footprints. So this video is going to be a bit advanced. This is not for someone who is starting their career in generative AI space. If you work for a global enterprise, this is going to be a very helpful video. If you are someone who is in school colleges, you probably might not need this, but you should have this knowledge. If you really want to do good in this space, you should have understanding of these minute details as well. All the global enterprises across the globe, they have sustainability as their agenda. They have to monitor, track, offset carbons, however. Okay. Now, these LLMs have cost memory carbon associated with them. Okay, so when we talk about open source LLMs, you have the control to find out, each and every details that you need, right? Memory consumption, what kind of GPU you need, how much carbon it has, and every other details that you need. But if you are using a closed source LLMs, it's very difficult. They have given some numbers, but you never trust those numbers. We don't even know how big the GPT-4 or GPT-5 model in near future will be, right? We don't have any idea about it. Now, this is going to be helpful if you are a strategist or an advisory role, or you are an architect working in the field of generative AI for a global enterprise. We're going to see how we can measure the memory consumption or memory required for inferencing large language models. We're going to look at Mixtral ATX22B MOE by Mistral AI, a French-based startup. We're going to look at Llama 3, the latest release by Meta AI, and Command R Plus. So these are the LLMs that we're going to look at it. We're going to make this a bit modular so anybody can use it from Hugging Face, and that's what the agenda is. Let's jump in into the video, guys. Now, if you look at here on my screen, I have a screen tab opened, and let me just write it over here. Okay, whew. And I'm going to write it here and say memory consumption. I'm going to first talk about a bit of the memory required, a bit theoretically, the formulas, because I have been reading a lot. I do a lot of research. I've been reading a lot of blogs, tutorials, research papers, and then I try to derive some findings from these and create videos. Now, it's going to be a bit theoretical, but we also code. We're going to code, guys. We are not going to load models. We are going to code and find out, without loading the model, can we find out the memory requirements? That's the plan. Now, three model I just said, right? So let me just write those models. So first it's going to be, for example, let me just write Command R plus. They have been performing really well on the leaderboards. Then we have MOE by Mixtral. So I'm gonna write it here. Mixtral ATX22B, or even uh, you know 7B as well. And then Llama 3. So Llama 3 has created havoc, in the open source community because they have been performing really well. One of the best LLM having the reasoning capabilities, guys. So that's fantastic. Now, these LLMs that when you see, they let me just change the color. All these LLMs, they are all distributed. Okay, so let me just write it. Distributed with 16-bit weight. They're all distributed with 16-bit weights, and for command R it's F16, and for these two guys it's BF16. Okay, so and I'll talk about it now. One parameter, and I'm show you one parameter. If you have one parameter in your model, that basically consumes 16 bits, or this becomes 2 bytes of memory. Now you should keep this in mind. Now, one parameter. Now imagine if you have 70 parameters, how much memory you probably need on a very high level. There are other things. We're gonna go deep dive into this, and then we also look at the code. But this is how this is the beginning. One parameter, 16 bits or 2 bytes of memory. Now 1 billion, if you have, for example, let's talk, if you have 1 billion params in your LLM. So 1 billion params occupy 2 billion bytes. So I'm going to write 2 billion bytes. Now, if you have 1 billion params, 2 billion bytes. Now, imagine if you have 7 billion. So you need 14 billion bytes. Okay, in that case. Now 1 billion byte, when you say 1 billion byte, is 1 gigabyte. Okay, so when you have 2 billion, it will be 2. So if you have, let me just write it over here, 1 billion bytes equals 1 gigabytes. So guys, you often ask this question. I have 4 GB, I have 8 GB in my machine. Can I inference this? Can I do this? Can I do that? So this is how you can calculate. Even Illuser AI has a very good blog. I'll give the link in description from Illuser AI. Now 1 gigabyte. Now if you have 1 B params, so you need 2 GB of memory in your machine. So 2 GB of memory, and we're not talking about VRAM as of now. So 100 billion parameters. Now if you talk about 100B, you need 200 GB of memory. This is what you need. But this is an approximation, guys, because 1 KB is not equal to 1000 bytes. It's 124. But I'm just taking an approximate number. So keep this in mind as well. Now, to know how many parameter a model has, let me show you. So you can find it out on the model card. Okay, so what I'm going to show you is, let me go to Llama 3 by Meta AI. Oh, I have to write Hugging Face. Okay. So Hugging Face indexing is still needs to be improved. If you look at this Meta Llama 370B, how many parameters it has, guys? It's listed over here, 70.6 billion params. Tensor type BF16, as I discussed it over here. If you look at this, the type of tensor. Okay, so if you look at this on my screen, here I have written BF16, and you can find it out the same thing for this BF16 model size. Now, if you want to find out Mixtral, let's look at Mixtral ATX22B, and I'm going to show you the base one, not the instruction tune. And 141 billion params, and this is also BF16, the type of tensor. So this is what I wanted to show you quickly. Okay, and if you want to do fast inference on GPUs, let's talk about it. Okay, you will need to load the model entirely on the GPU RAM if you want faster, because most of the time we need GPU to inference this, right? Because we want faster responses from the LLMs. So let me just write it over here and say uh, fast inference on GPU. How will you do that, guys? Now, if you need GPU, you need to load the model entirely on a VRAM GPU. So let me just write it over here. Command R plus, and how do we calculate all of these? We'll see that. Command R plus need around 193 GB of GPU RAM entirely. I'm not talking about any optimization technique, guys. Keep this in mind. We're not talking about any optimization. Mixtral ATEC 22B, and this requires 262 GB of GPU. That's really big. Too much of money to burn. And then Llama 370B, you need 130 almost GB, or a bit more than that. Okay, so these are the requirements, guys, of that. So you will need and the best GPU to inference A100 and H100. We all know that. These are the GPU that probably the entire industry uses it. So if you want to do Llama 370B, you need 2A into 100. This is what you need because it's 130. So one has 80. So you have 80 into 2, 160 GB of VRAM. You need 2A into 100 or 2H100 as well. So 280 GB. So you can do that. 2A100 or H100, whatever. I'm just calculating it's 80 GB of VRAM. Okay, that's it that it provides. Now let's talk about the important things, guys, which you should be aware. Okay, so memory consumption of activation, because it's all play of activation. So I'm gonna write memory consumption of activation. And you are someone who is not interested in looking at this theoretical knowledge or concept, feel free to skip this part of the video and directly go into the code later on. Okay, so we are gonna use Colab notebook to do that. Memory consumption of activation, but you will not be able to learn that way, guys. The best way to learn is to gain first the fundamentals and understand each and everything. Okay. Uh, Once the model is loaded, we have to activate functions. We have been learning this from our neural networks time, right? When we have been working in the deep learning neural network, CNN, RNN, LSTM. People nowadays have forgot, I think, the beginners, they're directly looking at LangChain and large language models. But see, you have to activate, you have to activate the model activations, right? So you have the function that you use to activate it, so you need memory to store. You need more memory to store the model's activations. Now, these are nothing but the tensor which are created during the inference. If you look at the tokenized dot in code, you will find some tensors, that there's some numerical values or the numerical representations when you print those variables. Now, tensors are passed because basically the tensor flows. Okay, if you look at tensor, they flows like this, right? The tensors are flowing inside. Tensors flow from one layer to the other layer or to the another layer. Okay, the next one, the size in memory is not straightforward, guys, to estimate, but we're going to talk about that. uh, there is a paper, let me show you that paper. Okay, let me just open that paper here. It's called reducing activations recomputation. Yes, this is the paper on, yeah, you can find it out here. uh, I will recommend you read this paper, this research paper. And I'm going to, it's by NVIDIA, you can see it's by NVIDIA, reducing activations recomputation in large transformer models, and I'm going to keep this as a base and discuss about it. Now, let's come back to screen grab over here and let's go in detail. We need few things. What are the things that we need? We need S are nothing but the sequence length, so I'm going to write maximum sequence length. Any LLM that you uses, it has a sequence length, a maximum sequence length, like 4096, 8096, 8024, whatever. Okay, maximum sequence length. Basically, this is nothing but the number of tokens in input, the input window. Okay, so number of tokens in input. This is what S is. Now, once you have S, you need B. B is nothing but the batch size. Okay, so B is nothing but the batch size. Then you need H. H are the hidden dimensions. You have to print the model config to understand these things. We're gonna print that. Okay, so I'm gonna writing here hidden dimensions of model. Hidden dimensions of model. And A is the number of attention head. Number of attention heads. Now these are the things that you need. So a standard transformer layer is composed of, if you look at the transformers, Andrej Karpathy has a fantastic video. I will recommend you watch that video. Now, a standard transformer layer is composed of a self-attention block, an MLP block, multi-layer perceptron, and each connected by two layers normalization, two layer norms. Now the memory consumption for each component is estimated as follow that I'm going to show you here. So let me just write it over for the self-attention first. So we're going to go block by block. So first is for self-attention, how I'm going to calculate. So for self-attention, write it over here. So the attention block consists of self-attention mechanism. So what do we have? We have self-attention, we have linear projection, L-pros, and attention dropout. And then we have attention dropout. Now, the formula is S multiplied B multiplied H, but S, B, H are nothing but the maximum sequence length, batch size, and the hidden dimensions of model. If you do S, B, H, okay, so I can also write SBH. Okay, so we're going to talk about that. So a linear projection retains its input activations, which have a size of, so let me just write it over here. For linear projection, it's going to be 2 into 2 multiplied SBH. That's the one. And both linear projection and self-attention input activation, they both require 2 SPH. Self-attention query queue and self-attention key needing 4 SH combined. So let me just write it over here. I'm just creating a formula, guys. So I'm just looking at it. Self query Q, I'm looking at my notes, and K, both required. Now it becomes 4 SBH. And then we have functions. So for example, if you have softmax function, then this required 2 into attention S square B and softmax function, and then it's a dropout. So for dropout we need 2a square b, and then we need a square b. Okay, for this, and then we storage. So storage for this is coming from the research paper, guys. The research paper by NVIDIA I was showing. Then this become 2a square b and then plus 2 SPH. So the total memory required. So let me just write it. This become the total memory. Now total memory required for attention block, and this becomes 11 SBH plus 5a square b. This is the total memory required for attention block. I'm going to write similarly for MLP block as well quickly, because we are going to do programmatically, but here I'm just writing the notes for you. I'll give this note so you can keep this handy. Uh, there's a industry recommendation when it comes to MLP block, and that is 19 SBH for storage. So I'm just writing it. I'll show you live in code when we are doing it. And and then next is activation memory. Activation memory for activation memory consumption for each layer or per layer, and this becomes 34 SBH plus 5a square b. These have been defined in the research paper, guys. That how. So basically they have 11 and 19. If you look at that, so they have 11 SBH plus 5a square b, and then they have 19 SBH from the MLP block, and then the 4 SBH from layer norms. So I'm just write it over here, layer norms, and layer norms had 4 SBH. So what we are doing, if you look at here, self attention is done, linear projection is done, attention dropout is done. If you look at MLP block, attention block and activation memory consumption layer, it all combines gets you 34 SBH plus 5a square b. And this is how you calculate it. Now let's go and calculate this. If you look at just for quickly, for example, if you look at the uh, S, for example, if a model has S as 512 as a sequence length, just taking a small sequence length, and eight batch sizes. These are the things that we defined. Okay, and if activations are 16 bits, so let me just write it out over here. Activations are 16 bit because we have talked F16 or BF16, and then we can compute it, guys. So if you compute, let me just get my graph here. Okay, so the activations loading the total becomes, yeah, I have already covered that over here. If you look at, if you come up, you'll find out this value 193 GB of GPU, 262 and 130, and we're gonna show that now through code. Now let's jump into the code and see how we can, you know, I'm not going to see how we can probably reduce the cost. Probably optimization we might do optimization later. Now let's come into and see how we can just do it programmatically. I'll show you spelled out in code. Now I have the memory consumption notebook opened. I'm going to take some gist, but the first thing that we're going to do is write some code to get the model. So from transformers import, we are not going to load model, we're going to use config. So I'm going to use auto config. So I'm just did from transformer import auto config, and the next is you can pass a model name. So let me just part model name equals, and I'm going to keep a model name. Let's get command R plus probably. Command R plus C for AI. Yeah, this model. It's by cohort for AI. It's by cohort, and you can take this. So let me just get this. Uh, yeah, command R plus model name is good. So we have our model name. Now what we're gonna do is model config. So let's get model config equals, and I'm going to do auto config dot from pre-trained, and this is fine, model name, and I'm going to print few things. What I'm going to print is hidden layers. So you need to know the hidden layers. So hidden layers are nothing but the model underscore config dot number of hidden layers. You can see it's called num hidden layers. I'm writing lawyers, excuse me. Hidden layers are good. Hidden size, model config dot underscore hidden size. And then we need attention head. Model config dot num attention head. This is fine. And then what I'm going to do is print. So let's print that. So I'm going to print the model name and model name str. We have to do string and just print model name, string hidden layers, attention heads, hidden size. And let me just write it a bit because we can use that in some formula, hidden layers. And I'm going to put that L and this becomes A because we're going to have substitute this in our formula, guys. Okay, now let's print that. It says model config is not defined. Oh, I've said mode config, excuse me. And you can find out it says the model, okay, config, model hidden layer 64, hidden size. We have here 12,288 and attention head of 96. Now in the below cell, we are going to, and I'll show you. Okay, let me just take the gist. I have created a gist already. So I'm gonna go on my gist, take it raw, Control A, Control C, come back over here and then paste. Now what we are doing, if you look at, it creates basically, also you can input it over here. We can also do it for, if you put that params here, no, it will do that. So let me just show it. Okay, so I'm gonna do is has, and let's write at param and type string. It will just create it, guys. Basically just to do a bit of data validation here. So the type string. So you can also input it if you want. And in case it's coher here, but if you want to try it out something else, you can just replace this. And here what we are doing, we are saying that this is the number of billion of parameters, 104, and then we have bit width model. We have a bit width. Let me just close this, not required. Bit width model 16. So we are printing it out. You can see bit width optimizer, sequence length, and batch sizes that we discussed here. Now let's just run this. And if you run this, it basically prints the same thing that we are printing. And now we are going to calculate. So what we're going to do, we're going to run the one more cell. So I've already created gist for that. No, not this one, excuse me. If I have not created gist, then I have to write the code. Okay, let me just quickly see it. Yeah, calc.py. Yes, this is the one. Now I have a function that calculates it basically. So let's use that function here. Now what we are doing, if you look at in this function, we're saying define estimate consumption. And then we have the same formula that you see, 34 SBH plus 5A square B, and then return round, define estimate optimizer size, model size, and just activation. So we are getting activation consumption, model consumption, and optimizer consumption as well. We are also having optimization here. And if you print that, and let me just make it a bit bigger so you can read it. Now, if you read this, says memory consumption of the model 193.72 GB. Now, you can also build an app, guys. Probably we can build a Streamlit app, put it on Hugging Face Spaces or GitHub, so people can try it out how much memory they need. Memory consumption of the optimizer, you can see 77 for memory consumption of activations for fine tuning, total memory consumption for fine tuning, memory consumption of activation for inference 5.6 GB, and total memory consumption for inference is 198.78 GB. So this is how you basically calculate how much memory it will require for you to inference. There are different techniques, guys, that will help you reduce the memory consumption. I have discussed that earlier as well in my different videos. I can give link in description, you can go through it. You reducing the memory consumption mainly for fine tuning. You have PEFT techniques like LoRa, QLoRa, DORA, blah blah blah. Okay, you can use all of those, and you can also use different types of optimizer like Adaptfactor, Adam 8-bit, and now we have Galore by Transformers. I mean, not transformers. Now we have Galore, which basically supports the transformers models, and basically it's project the gradients into low rank subspaces. So it reduces the memory consumption by 80%, which is really good. And this is what I wanted to do. I wanted to show you how you can do it. Now feel free to take this notebook and build some Streamlit application, host it on Hugging Face Space, where I can do it, where you just have to pass the model name and bunch of input params like billion of parameters, bit width model, bit width optimizers, sequence length, batch sizes, blah blah blah, and then you get the uh, how much memory it is required for that model consumption. So if you have any questions, just let me know. I'll recommend you read this research paper if you want more detailed information on this. But if you have any question, thoughts, feedbacks, let me know in the comment box. I'll give the notebook and the screen graph of the tab where I was writing, explaining theoretically, and I hope you got a basic understanding. These fields are really vast, guys. This video is just for you to get started. These are really deep. You can optimize each and every processes in this workflow to cut down the memory cost and things like that. If you like the content I'm creating, please hit the like icon. And if you haven't subscribed the channel yet, please do subscribe the channel, guys. That motivates me to create such more videos in near future. That's all for this video, guys. Thank you so much for watching. See you in the next one.